will deliver his first lecture on Ramanujan complexes.
Thank you. So first of all, thank you very much for the organizer for inviting me, and especially thanks for the organizer and the previous speakers who kind of set me up in a beautiful way. There was I was asked to describe some topics in the theory of high-dimensional expanders and also Ramanujan complexes. And I should say that if I were to give the first talk in this conference, then a lot of what I would say there would be a lot of black boxes. I would use a lot of representation theory. And thankfully, Indira and Anne-Marie put a lot of the preliminaries needed for my talk. So thank you for that. And also, my three talks will be independent from one another. Well, the first one will definitely be independent from the other two. I would like to tell you today how to generalize the notion that Alan described in his talk, the Ramanujan graphs, to higher dimensions. And in the next two talks, I will describe what are high-dimensional expanders, which are not just Ramanujan complexes. And so if you kind of get lost in this talk, that's fine. It's actually part of the plan. When I get to the third topic, it will be pretty advanced, but I think you should at least hear it once, even if you don't understand exactly what are. So here I will do what my predecessors have decided not to do and talk about Adele's automorphic representation. It's going to be rough, but the first two are completely should be completely accessible. Okay, so what are Ramanujan complexes? So we know what are Ramanujan graphs. For complexes, I will need the theory of Bruhat-Tits building. So let's F be the group of F points group of a reductive algebraic group defined over F, non-Archimedean local field. I'll give examples in a minute. B will be the Bruhat-Tits building. Of G. So in particular, G is a subgroup of the automorphism of the buildings. Gamma will be a co-compact lattice of G. So in particular, it's also a subgroup of the automorphism of the building. And on the node by X, the quotient of the building by the action of gamma. And because the lattice is co-compact, this is in fact a finite quotient of the building. Well, why is this finite? So let's look at the maximal faces, and let's convince ourselves that the set of maximal faces of the quotient is finite. So this is the set of chambers in the building divided by gamma, and by Petra's talk we know that essentially, ignoring cases where we act non-color preserving, the chambers are identified with G modulo d Vahori, and the maximal faces in the quotient can be identified with the double cosets. And just note that on the one hand, the Vahori is an open subgroup, so this should be discrete when you divide by an open subgroup. And on the other hand, our lattice is co-compact, so this should be compact. So compact and discrete must give us something that this is finite. Okay, And if there are only finitely many maximal faces, then there are only finitely many faces. And an example to keep in mind for the rest of the first part of the first lecture is, let's take, I prefer the group PGL2 over the p-adics, but if you want, SL2 will work just fine. And the building, as Petro described, is the p+1 regular tree. And what we get is that X is a finite p+1 regular graph. Any co-compact lattice of PGL2QP will give you a finite p+1 regular graph. And yes?
Are you assuming that gamma acts without stabilizers on the...
Ah, yeah, thank you. I told you why. No stabilizers, no analog of O before this. Thank you. And here's a nice exercise for you to think. If the lattice was not co-compact, what would the quotient be in the case of the tree? Geometrically, think of what should we have? Okay, so now the definition. So in order to define what are Ramanujan, so let me say briefly that for graphs, to define what is a Ramanujan graph, we need an operator, the adjacency operator. We needed its spectrum, and we needed a notion of the trivial eigenvalues. We wanted to exclude them and to say that the rest belong into some domain, into some segment. Okay, so I need to. Already, I face my first challenge. Where for graphs there is a natural operator, but for buildings there are many natural adjacency operators. So let me begin by saying that an operator T on the building is called geometric if it commutes with the action of the group. The natural action induced by how the group acts on the building.
What exactly is L2 of B?
Ah, thank you. So L2 of B, first of all, B you can think of it as a disjoint union of the different faces. And so L2 of B I could just as well think of it as the disjoint union of each face. And for each dimension, well, this is just the set of all the functions, complex value, and I want to put the natural inner product, and so I want to make it into a Hilbert space. So it's the analog of the L2. So if the building was, say, a tree, and we wanted to calculate the spectrum of the adjacency operator on the tree, then we had to consider the L2, the space of L2 functions on the tree, and then compute its spectrum, and then we get Kasten's theorem. If we don't take the L2 space, then there are many more eigenvalues.
So BI is the collection of all I-dimensional phases?
Yeah, I.
Just makes sense.
Yeah. So you see, even though the speakers behind me did a wonderful job, I still, there are some notations here that I-dimensional faces. And I think it also proves my point that you see there's so many, because it's high dimension, you need to remember there's so much freedom. Operators on which dimension? Are you talking about operators on the vertices, on the maximal chambers? And the answer is you should probably consider them all. Okay, so it's called geometric if it commutes for any G. If T is geometric, then note that it induces an operator on the finite quotients for any cocompact line. Okay. So this is a notion of a geometric operator, and now we denote by spec T restricted to X and spec T restricted to B, the spectrum of T on the complex or the finite quotient or what it's building respectively. So we're almost done. I can almost define what is a Ramanujan complex, and there's one thing missing. I also need to denote. By the way, X is finite, right? This is a fancy, I think Indira might dislike this notation because this is a fancy way to say just complex function on X. With the standard in a product, there's no really L2 space needed here. And so this spectrum, it's an operator on a finite dimensional complex vector space. So this is comprised of eigenvalues. This is an operator, bounded operator on a truly L2 space, and so the spectrum here is continuous, just like in Alain's example of the
switching to B is just to remind us that it's on B, because T is on L2. No?
So T is on L2 of B, but I'm saying that if it's geometric, then it's also descending to operators of
Yeah. No, I'm saying just the notation spec T restricted to B.
Yeah, I just don't want to carry the L2 in the notation.
Okay.
Yeah, so T restricted to X means the induce of T on the space L2X, and T restricted to B means T on L2B. And please stop me to ask questions if I'm going too fast or something's not clear. Okay. The final things I need in order to define what the Ramanujan complexes are is to denote the subset of a non-trivial eigenvalues. Where I called an eigenvalue of the operator on the finite quotient trivial if its eigenvector is fixed or is invariant under the action G prime, which is the subgroup, the type-preserving subgroup of G, the maximal type-preserving subgroup. Okay.
By type preserving?
So the building has a natural coloring or type function. You can usually just take the commutator subgroup and just be done with it. I think in almost all the cases, this is the only group that you can. And I'll show an example in a second what happened in this case. It will be, okay, I'll tell you the other, so it's PSL2. So
what you mean is that the eigenvector, when lifted to the building, becomes invariant.
is that what I mean? I mean that you don't necessarily need to lift it because on L2, wait, you are correct, sir. Yes, thank you.
But you have to, right? I mean, G acts on L2 of V.
So technically not. G would act on L2 of G mod gamma. I'm kind of using the action of G when I quotient from the left by gamma. There's no more, G can no longer act on this set. That's it. Okay, so now here's the definition. A quotient is called Ramanujan if the non-trivial part of the spectrum is contained in the spectrum of the building for any geometric operator. And let's return to our specific example where G is PGL2QP. And then T you can take as the adjacency operator on the vertices. And you can ask what is the spectrum of T acting on the P+1 regular tree, the building, and this is by Captain's word. It's equal to the Ramanujan segment. You can ask what are the trivial eigenvalues, or first, what is the group that acting type preserving, because this group sends a vertex of type 0 to a vertex of type 1. This group actually acts transitively on the vertices. There are two types of vertices. So it has a subgroup of index 2 which acts transitively on the edges, acts transitively on the vertices of type 1, and acts transitively on vertices of the other type. And the trivial eigenvalues, well, the trivial eigenvectors, any vector which is G tag invariant must be constant on the vertices of type 1 and on the vertices of type 2. And so what you get is that the only possible eigenvalues you get from such functions? Well, if the graph is non-bipartite, you only get p plus 1. And if the quotient is bipartite, then you get an extra eigenvalue, the minus p plus 1, because you can be constant on one side and constant on the other side.
So Shai, is that spec 0, what you wrote there?
So this is not spec 0. Let me reiterate. On the building, I don't define the trivial eigenvalues because the building don't see the trivial eigenvalues. Just like the infinite p plus 1 regular tree does not have p plus 1 as an eigenvalue. It has, its quotient has the p plus 1 eigenvalue. And so what I get is that Ramanujan, or the quotient is Ramanujan, if the spectrum if I remove the trivial part, is contained in the segment which is the spectrum of the building. And now some of you might ask rightfully, well, you just show it for one geometric operator. What about the rest? Well, for 3, there's not a lot more eigenvalues, operators which are geometric on the vertices. All of them are polynomials in T. And you should say something about the edges, but I was told you wanted exercises, so. Okay. So this is how you generalize the notion of Ramanujan graphs to higher dimensions and quotient of building. Yes? Any questions?
Does every p plus 1 regular graph arise from a lattice?
Yes. Yes, you can, any p plus 1 regular graph, you can just look at it as a topological object, as its universal cover is the p plus 1 regular tree.
Yeah.
And so its fundamental group is a subgroup of the automorphism of the tree. So what you get is a lattice in the automorphism group. Yeah, of the tree. Now what's okay, so this is the geometric / combinatorial definition, but in practice, most of us, I think, work with a representation-theoretic definition of when is a quotient or Ramanujan graph. So let me recall some notation. So now we are in the local representation theory. Of G. Okay, so I'll conform to the notation from Indir's book. G hat will be the set of equivalence classes of unitary irreducible representations of G. And for any such an irreducible representation, I can associate a number to it, the rate of decay of matrix coefficients. So if so in Indira's talk, she was telling you that the property T is saying that the trivial representation is isolated from the rest. And the definition was topologically. There is an open environment in which T sits alone. But you can actually measure it, at least for algebraic groups over local field, you can measure it with specific numbers saying how far it is from the rest. And you do it by something called the rate of decay of matrix coefficient. So it's the infimum among all numbers between 2 and infinity, including 2 and infinity, such that any matrix coefficient, and here you should probably do some technical condition, but don't worry about it. Any matrix coefficient of the representation as a function of G sits in L R of G. Its alpha power is integrable with respect to the half measure on G. So, for example, for the trivial representation, we get that the rate of decay of matrix coefficient is infinity. The matrix coefficients are constant, so you cannot just integrate them, no matter which power you take. Okay, and we say that we call such a representation tempered if its rate of decay of matrix coefficient is exactly 2. And I need to insert the notation, so let's call it G hat T, the subset of tempered representation. And this would be an important subset for us to consider. Okay, let's just for the sake of notation, I will denote in the eval side.
Out the definition of R of sigma again, it's difficult to read.
Ah, yes. So you take the infimum among all the R's between 2 and infinity, and such that any matrix coefficient of the representation, and let me just remind you, a matrix coefficient of a representation is a function of the form so it's a function from G to the complex numbers. You send G to the inner product of pi G V U, the inner product in the unitary, not pi, but sigma. Sigma is a unitary representation for some fixed vectors of the representation.
Yeah, now you left out the thing that's discrete and so is unusable. And
This is, yeah, I don't want you to see it because there should be some small conditions because there might be a very few number of matrix coefficient which might not satisfy it, but
The definition is definitely, the condition is definitely small.
It's K finite.
K finite, yeah. And K is a compact subgroup. Yeah.
And do you ever do square integrable representation?
So if, yeah, every square integrable representation would live, will be tempered, but yeah, not, I don't want to restrict only to the square integrable representations. Okay, so now, what kind of representations interest us? So again, gamma is a co-compact lattice. So it gives us a non-irreducible, highly irreducible unitary representation a semi-regular or quasi-regular representation, which I usually denote by simply writing the space on which it acts. It acts from the right. And I want to, okay, so first things first, so what do we know about this representation? So this is a unitary representation. Because G mod gamma is compact, it's easy to give an inner product. And in fact, Anne-Marie discussed this representation in her talk, and this representation has a discrete decomposition and denote the set of its irreducible factors by, call it the spec L2 of G mod gamma. Is a subset of the irreducible representations appearing in the discrete decomposition of this presentation, and also denote the subset of infinite dimensional. There are very few. Let's say if G was simple, there are very few finite dimensional, they're usually one-dimensional representations of G, and I want to exclude them. So I'll, keeping with the notation from before, and I'll add a subscript 0 to denote the infinite dimensional representations appearing here. And finally, for the sake of determining whether the quotient of the building by gamma is Ramanujan, I don't really need to know, I don't need information about all the members here. I only need to know about the Ivahovi spherical representations. Now denote them by spec 0I L2 G mod gamma. So these are all the members from before, from infinite dimensional, and such that they have a non-zero vector fixed by the whole subgroup. And now here's a useful characterization. So the quotient is Ramanujan if and only if the irreducible factor of these representations, which are infinite dimensional and Ivahori spherical, are all tempered. How did I do that? Okay. Okay. And now, proof exercises. But I give you hints because it's something that you should do to get familiar with the dictionary between representation theory and eigenvalues. So first things first, you need to see that geometric operators are Ivahori operators. So now I know there are, let me just remind you that our quotient, the space of function, L2 function of the quotient, let's say that we only consider the maximal faces to make it easier, otherwise it's the same idea, but it simply becomes a bit more technical. You need to decompose, and according to each dimension of face, you might need to consider parahorics and not just the Ivahori subgroup, but there's nothing more complicated than that. You need to realize your space as the space of these double cosets. And the Ivahori operators are related to what Petra mentioned at the end of her talk, that there are these forgot the name. How should I say it? There are these contractions, and those were the inverse image of the contractions actually gives you natural geometric operators on the building. So for instance, you can consider this indicator function of the double Ivahori.
Right?
Sorry?
You mean retractions?
The retractions, yes. Yeah, so I want, so in this retraction, so you can basically define geometric operators or Ivahori operators using retractions. So you start with some element, and you want to average all the neighbors whose after retraction they are of distance w from that element. So this operator acts on L2x, which is L2 of G mod I mod gamma, by for any function, you just gxwi, gxwi runs over wi and b infinity. So it's a convolution operator from the right. So this is one dictionary. Another dictionary is to show that the eigenvalues actually lives inside the I-spherical irreducible representations. The eigenvectors actually are vectors sitting inside I-spherical irreducible representations to show that trivial is nothing else than finite dimensional representations. And the most interesting part, the spectrum of the building are exactly the temporal representations, which is not that surprising given the fact that the building itself you identified with G mod I. And if you want to be a function on an L2 function of the building, well, your matrix coefficient should probably be very close to an L2 function. Okay. Okay, so I have 7 minutes, right?
Yes.
Okay.
So what do you call the spectrum of the building?
Yeah, so it's the spectrum of the building. So any eigenvalue here would correspond to an I-spherical irreducible representations. And the only so if you have an eigenvalue, if you have an I-spherical irreducible representations that contribute an eigenvalue, or not an eigenvalue, contribute to the spectrum of the building, then it must be tempered. Because what is tempered? Tempered are those whose matrix coefficients are almost an L2 function of G. Almost. You need to add some little bit of wiggle room. And so if you have an element in the spectrum, you can approximate it using almost eigenvectors. Those functions will be here. They will be I-spherical, so they will actually be here in the functions which are almost square integrable on the building. And that's essentially the proof. You want to, that's part of the exercise. You need to do it once and then you are done with it for
Will you or some other speaker give an example of a non-tempered irreducible representation?
the non-tempered, I mean, we have good examples. Sorry? The trivial, yeah, but there are some interesting non-trivial which exist for arithmetic reasons. We need to talk about
In PSL2?
for PSL2, just the complementary series, just things which are not tempered. Yeah, there are many representations. They don't usually. So remember that we have this segment which sits inside the bigger possible spectrum. So every eigenvalue here, outside of the Ramanujan segment, will give you an irreducible representation. I-spherical, actually I can make it to be an unramified principal series, which is non-tempered. It has a name, it's called a complementary series. To get members here, in the case of graphs, you need to start with, I'm now saying it in the language of algorithms, you need to start with the torus, and you take a character, but you take a unitary character, and you take the parabolic induction, and you get somebody here. But what happens if you take a non-unitary character? Well, often or not, you might not get a unitary representation, so it doesn't really matter. But there are cases where you can take a non-unitary, unramified representation, where you can give it the structure of a unitary representation, it will contribute outside. These are the complementary series, complementary to the principal series. Complementary to this. Okay, so it might be pretty good that I didn't have the opportunity to tell you about the the Ramanujan conjecture, because it's kind of technical, but let me just, I do want to say something in the last 5 minutes that I have. So I'll try my best. So what kind of representations appear in this composition? So first of all, yeah, okay, so I'll just say it briefly. So, for a special case of lattices, the congruent subgroups, these are the special case of the lattices. One can use global representation theory. To give bounds on these collections, this collection of representations. So if you just tell me gamma is a co-compact lattice, I don't know how to say much. I know how to use property T, but that's about it. But if you tell me that this subgroup is a congruent subgroup, then I can in fact say more about these sets. And maybe I'll just state it in this language. I can now state the naive Ramanujan conjecture. And I actually don't need the adels to state it like that. So if gamma is congruence, then this is contained in the and I need except the finite dimensionals. They are obviously they're not tempered, so I'm excluding them. Then I get that everything here is contained in the tempered spectrum. So be careful. Remember the word here. This is not true in general. There are cases that one can show that it is true, and those were the cases coming from division algebras, much like the construction of LPS using quaternion algebra. You can use higher dimensional division algebra and to concoct situation where your group satisfied this property for all congruent subgroups. And these were how Ramanujan complexes were constructed in the early 2000s. But it doesn't hold for all groups, so this is false in general. False in general, but when it holds, you get Ramanujan complexes for free, right? The corollary of this conjecture when it holds is that we have a lot of Ramanujan complexes coming when we take gamma to be congruent. Okay, so I think I'll stop here. Thank you very much.
Thank you very much. Any questions? Yes?
What do you mean by Ivahori operator?
An Ivahori operator is okay, so let's look at this vector space. So an Ivahori operator, which I think I denoted by an implicated function of a double Ivahori cosets, is, so these are like the atomic Ivahori operators. You take any function here and you let this act from the right. So this, what is a function here? The elements here are double cosets, so I cosets from the right. So you can write here for all yi in xiwi, you average, and this has a geometric interpretation using the retraction from Petra's talk. You kind of average over all the pre-images of the retraction. And the Ivahori operator in general, you can take sums of these operators. And also, if you don't want to act on the top faces of the chambers, you can, on the intermediate faces, you need to replace I with a parahoric subgroup. And this is like a generic name that kind of captures all of these operators in one.
Other questions? If not, then before we thank the speaker again, maybe you want to say something about the afternoon or the dinner? Because we got an email, but I know maybe not everybody reads them.